by starting with the real basics of OpenMP and then moving into some slightly more advanced things and basically some hints as to how to get better performance out of OpenMP and some other advanced topics. So the basic outline of this part of the talk is we'll start by covering some real basics of threaded programming and what our assumptions are for what your background is, give you a real top-level introduction to how OpenMP works, show you how to create threads using OpenMP, discuss some of the issues with synchronization, show you how to parallelize loops, and then get into some of the more detailed topics and how to use different types of synchronization and how to use the data sharing attributes. Basically, having looked over the program for this week, we're assuming that you already have some knowledge about parallel architectures and about parallel programming in general. So certainly, given that you had an extensive day of MPI programming, I think that part is fair. We're also assuming that you have some idea of what a thread is and what cache coherent address spaces are. So if you touch data in one processor, you'll end up seeing it in the other processor. And to a very small extent, we're sort of assuming that you know something about Pthreads, although really not so much. We'll start with an example of showing how you would use Pthreads to parallelize a simple code, and we're not going to go into the details of Pthreads, is really what that means. All right, so the example we're going to use this morning is a very simple one, numerical integration. So what we're going to do is basically, this is this simple example for how to calculate pi. We know that you can calculate it with this simple integral, and as with any integral, you can chop up underneath the curve into a bunch of rectangles, calculate the size of increasingly smaller rectangles, and you'll get a pretty good approximation of the integral. All right? And so we just need the width of those rectangles and its height. This is pretty easily turned into a serial program where we chop the interval into some number of rectangles, and now we figure out how wide each of those rectangles is. Now we're going to go across that, back across here. So we're going to advance x and start with it being just the rightmost interval, center. We'll increase it each time we do another step, and we'll just add up each of those pieces. Simple enough. All right, and in the end, we just say, okay, now we have the total of the heights. Boom. There's our estimate of pi. So if we wanted to use Pthreads, which is a very low-level thread programming API, how would we go about turning this into a parallel program? Well, first thing is we're going to take this loop here and move it into a different function. All right? So that way we can actually execute it in each of the threads we create. But we have to make sure that this sum is shared so that we get, as we increment the sum in each of the threads we're going to create, we get it shared, we get the value incremented with all of the additions. And then we just need to give some of these loop iterations to each of the threads we create. And one last thing is we need to make sure that we update sum safely, because if we update it with a race condition, the result could be undefined. So first thing is we take that loop out and we move it to a separate function. So here it is, func. We put these global variables, and we're also going to add a lock variable here. All right. Now we're going to distribute each of the iterations of the loop, and we're just going to do it in a nice cyclic distribution. We'll just here's an iteration for you, here's an iteration for you, here's an iteration for you. So as I said, we have to make sure that the sum is updated safely, so we're going to put that in a critical section. So back to the main program, we have to initialize that lock variable, the mutex variable. Then we have to create each of our threads. We're going to go and create a thread for each one, and that's going to each of those threads will execute that function that we just defined. After while they're all executing, we have to make sure they're all finished. And then down here, we're going to wait for them all to finish, so we're going to join them. And that way, we're guaranteed now all the threads have completed. And now we can get rid of the lock, And finally, we have our value of pi. We started with this nice simple program, fairly complicated program now to parallelize it. Right? The way we did it is we used the fork join pattern, right, which is one of the most common parallelization mechanisms. All right? So basically all you do is you take a serial program, and when you want to do work in parallel, you pack it into a function, and you fork a number of threads to execute that function, and then when each of the threads, when the functions have completed, you join those threads, and now you're guaranteed that all the work is done, and now you can go back and run as serial. So this is a pretty mechanical transformation to your code, but it took a lot of work to go and introduce it there using PThreads. Well, you can do that a lot more easily using compiler transformations. Because it's so mechanical, it's very easy for a compiler to understand how to do this if you can just describe where to do it. Right? And that's what OpenMP allows you to do. You know, it's useful to have the URL. This is a bunch of different stuff that OpenMP provides. So what OpenMP is a bunch of compiler directives. So a bunch of ways to describe to the compiler how you want to parallelize the program. And then there's also several library routines for things that you might want to get information about, how the compiler is actually parallelizing your program, and also other ways where you want to instruct the compiler, not just for this piece of code, but in general how I want you to behave. There's actually a runtime underneath there, which I'll explain in a minute. So this makes it a lot easier to write multi-threaded programs, right? And OpenMP applies to Fortran, C, and C++. So it's kind of a meta parallelization language in a way. So going back to the fork join pattern, the way this basically works is you have a master thread which goes and forks off threads to execute parts of the program in parallel. Then they all join, and you execute in the master thread again. You go along, and so now you have multiple parallel regions. All right? And so this way you can actually incrementally add parallelism to your program. All right? So this is actually one of the advantages of OpenMP compared to something like MPI. If you parallelize your program in MPI, your whole program is parallelized. All right? Whereas in OpenMP, you can gradually decide where you want to add parallelism. There's pluses and minuses to that. I won't go into the details of it. But what you want to take away is that you don't have to worry about how to parallelize the entire code. You can just parallelize specific regions that you know are already computationally intensive, and you expect to get some benefit out of using more processors on it at the same time. Some of the terms that you'll hear thrown around in OpenMP, one of the big terms you'll hear is the sequential part of your program, all right? And so that's just where you don't have any parallel regions, all right? In fact, in OpenMP, we call that the implicit parallel region, but there's only one thread that's executing it. Now, we already mentioned that you have these parallel regions, and in fact, in OpenMP, you can have nested parallel regions. So you could be going along in one of your threads and decide, oh, I actually have even more work, and I want to have more threads work on it, so I'm going to create another parallel region within that parallel region. As I said, OpenMP is primarily implemented as formed through compiler directives, all right? And so in C and C++, those directives take the form of pound, pragma, OMP, and then the construct name and potentially a number of clauses. Probably the most basic example is how you go about creating a parallel region. So you say, the name of the construct is parallel, and one of the clauses that's available for a parallel region is the num threads clause. So this would tell the compiler, create a parallel region at this point in my code with 4 threads. In addition, as I mentioned, there's several runtime library functions, and there's also a few types for OpenMP, and you get those by including omp.h. And there's similar syntax in Fortran. To me, Fortran is a bit of a foreign language, so for those of you who it's your native language, I'll just let you worry about how to do it. But it's basically exclamation point, OMP, and then pretty similar after that, all right? And there's Fortran modules that you can pull into your code as well. A key aspect of OpenMP is that it has this concept of a structured block, which is says, I've added this directive. What does it apply to? All right. Well, what it applies to is a structured block. And what is a structured block? Well, it's in C. It's really one statement. All right. And if you want to have it be more than one statement, you use braces to turn that set of statements into a single statement. But importantly, when you have a set of statements, then you better make it so that you can only enter that set of statements at the top of the block, and you can only exit it at the bottom. All right, and there's one exception to that, which is that you're allowed to call exit within the structured block, but you can't call return, for instance, right? Because that would give you an exit from the structured block that still leaves the parallelism going. So the reason that this is allowed is if you exit out of a structured block, you're ending the entire program. But if you were to return out of a structured block, the compiler would be leaving the threads going, and now the mechanisms by which the compiler manages the threads have been somewhat subverted. All right, so OpenMP ends up having, as with everything in computer science, a stack that is how we actually end up implementing it. Here's you and your application using OpenMP. We have the directives and the library, and we also have environment variables that allow you to control how the OpenMP works. All right, that's then implemented. The compiler will turn your directives into code, as I'll go through a little bit here, but also with a runtime library that then manages creating threads for you, making sure that you get the number of threads you wanted, a variety of different functions, managing whether or not you can have nested parallelism. And then that's then built on top of support within the operating system or the system software in general for shared memory and threading. The OpenMP runtime library might actually be built on top of PThreads. That's a very common mechanism. Oftentimes, the most efficient OpenMP runtimes go and use even lower level thread implementations in the operating system. All right, so how do threads interact? All right, so in MPI, if you want to have information communicated from one MPI process to another MPI process, you have to explicitly send a message. In threaded programming, you're actually able to access the same memory location, right? So you can share variables. And in OpenMP, what we actually have is a concept of shared variables that I'll explain shortly. In general, if you're only reading the data between multiple threads, that's a good thing, all right? You don't have to synchronize accesses if you're only reading it, because there's no chance of getting conflicting data written, or trying to read data and not getting back the most recently written data. On the other hand, if you are writing the data and you aren't aware of or aren't careful with how you write it, you can create race conditions, all right? A simple definition is when the program's outcome changes as the threads are scheduled in different orders. The slightly more complicated definition is that you have multiple accesses to a variable by different threads without synchronization, and at least one of those accesses is a write. As I've kind of already said, the way you avoid having race conditions is by properly synchronizing your program. However, in general, when you synchronize, that involves writing other data, and typically that data is more expensive to write because it's sort of special data that allows you to write without having synchronization, all right? So you want to avoid synchronization whenever possible. So you end up wanting to alter your code slightly oftentimes in order to minimize that synchronization. All right, so how do we create threads in OpenMP? So as I've already gone through, we have this fork join pattern. We're going to be generally often running in sequential parts, but we'll come to places where we want to add parallelism, so we're now going to create a parallel region. So as I mentioned in that one example, with that one construct that was shown in the earlier slide, you use the parallel construct in OpenMP to create parallel regions. So what's going to end up happening is each thread is going to execute a copy of this code, of this structured block. And here's a simple runtime routine. The set num threads routine that says for all OpenMP parallel regions, use 4 threads. And so that's what we get here. Is this says from now on use that certain number of threads. And here's another runtime function that says, well, I created 4 threads. Which thread am I? All right. And so now it just says each thread is going to call that function, and we'll get 4 copies of it. Okay, so it's important to realize that each thread is going to execute that code redundantly. You need to do something to make it so that it's useful to have it executed in parallel. Otherwise, you're just doing redundant work. But what happens is you come down here, and as we said, they fork off the work to 4 different threads. Each of them now has a different thread number, different thread ID. Once they finish executing the functions, they're going to join up. Okay, so what does the compiler do when it encounters this? All right. Well, it's actually going to extract the code in the structured block and put it off in its own function, just like you were doing with PThreads. And it's going to go and create a number of threads. All right. Now here you'll notice that it's actually only creating 3 threads, and each of those threads is going to execute this function that it created, which is again exactly what you did in PThreads. One difference is here we're going to actually have this master thread is going to execute the function as well, because we've already got a thread there. Why not use it? When we get down here, the master thread has finished executing its call to a function, and we want to make sure the other 3 have finished executing theirs, and there you go. All right. And then this shows you basically how we can actually make the compiler recognize these directives. All right. Compiler directives are useful because if you want to ignore them, you just don't pass the option to your compiler that says interpret those directives, and then you have code that executes in serial. All right. But you pass these different flags, and now you can actually get it so that you'll compile it in parallel. All right, so if we wanted to create a parallel version of that Pi program using just a parallel construct, how would we go about doing it? Well, we're going to have to make sure we pay close attention to which variables we want to be shared and which we want to be private. And we also need a couple runtime routines. We've already seen the get num threads clause and get thread num. We've seen the set num threads and the get thread num. And there's also one that says, okay, how many threads did we actually get? So we can go and find that out. And then finally, there's a function, much like we have in MPI, that lets us get time, so we can actually figure out how long things take. So here's our serial program again. And so we can go and add a bunch of stuff to it. So first of all, we're going to go and include omp.h so we can actually access those runtime functions. We're going to define a macro that says num threads is 2. We're going to set the number of threads to 2. But we're going to turn this sum into an array, all right, in order to avoid race conditions. So we can go and access it, but we don't have to synchronize every time we do. We put in a directive that says, hey, execute this chunk of code in parallel. We go and in each one we say, well, what thread number am I? How many threads did I actually get? If my thread ID is 0, set this variable so after I exit the parallel region I can know how many threads I actually got. Now go and once again execute all of these iterations, dealing them out across the different threads like a deck of cards, basically. So we've just gone and created a nice cyclic distribution there. All right, and then at the bottom we're going to add them all up and get the final value. So that is an instance of an SPMD, single program, multiple data parallelization. All right, so we're actually running the same program on each of the P processing elements, each of our threads, and we can make P as arbitrarily large as we like. We then use the rank or the thread ID to understand where we are in that range of parallelism. So this is a very general pattern. If, we'll assume you've probably seen it before, but you want to keep it in mind. I'm sure you've seen it before because this is how MPI really works in general. MPI is not strictly an SPMD programming model, but almost all MPI programs end up being SPMD programs. All right, so how did we do? So the serial program executes in 1.83 seconds. So we've parallelized this. We've used 4 threads on a machine with 2 cores, but 4 hardware threads. And we get not quite a speed up of 2. That's not too good. Well, what happened is we got something that we call false sharing. And if you're not familiar with this, if you're going to do threaded programming, you need to be familiar with this concept. And basically what it is, all right, so we spread sum over an array, so that way we wouldn't have to synchronize each access to sum. And so cache coherence hardware of the processor, of the node, takes care of making sure that we don't have race conditions. Each of the sums is typically going to, a single cache line will hold multiple integers. All right, so now, or multiple doubles, whatever we have. All right, so now, even though when we access sum 0 and sum 2, we don't have a race condition, what we do have is that we can't write to this cache line if this guy has write ownership of it. So we invalidate it over here, bring it back over here, and back and forth, back and forth. All right, so we're creating a lot of traffic to make sure that we don't end up having any race conditions. So what can we do? The simplest solution is, well, we can just pad the arrays, right? If we put this in a different cache line and that, then we won't have a problem. And so we'll try that. We'll just go and pad the array. So now each sum value is in a different cache line, and that then means that we have to access sum a little bit more complicated, but not too much more complicated. And if we do that, we get actually pretty good scaling now. Not quite a speed up of 4, but better than 3. Well, so far, we turned the simple program into a parallel program, and we avoided having to do any synchronization in OpenMP, which is generally good, but sometimes you just can't do that. All right? So we need to be able to understand how to do synchronization, and there's several synchronization concepts in OpenMP. I'll start with these. There's actually more than that now in OpenMP, but we'll maybe touch on some of those later today. All right, but so there's high-level synchronization concepts. We have critical sections, atomic sections, barriers, ordered constructs, and then low-level synchronization, flushes, which I will advise you to avoid using explicit ones, although there's implicit ones all over the place that need to be, and then locks, and you can have both simple and nested locks. And all of these will be discussed later. I'll tell you right now about some of these other ones. One of the most common reasons for using synchronization is to provide mutual exclusion, which means that only one thread is going to be able to access this region of code at a time, all right, and basically access the variables that are being touched in that region of code at a time, all right, and that's called a critical region. So each thread, if we add the critical directive here, all right, we now say this block of code, this structured block, this one line, is a critical section. And so when we come along here in OpenMP, a thread is executing this, it's going to, within the runtime, say, are any other threads inside this critical region? If not, then this thread can go ahead and execute. All right. So under the covers, the runtime is basically going to create a lock for you that manages access here, and it's going to try and obtain that lock, and when it gets the lock, it's going to allow that thread to go ahead and execute. All right. Now it's holding the lock, so when another thread comes along, it can't get the lock until it finishes executing and releases the lock. All right, so atomic is very similar to critical. The difference is that it only applies to the update of a memory location. And this is the simplest form of atomic, which is the update form. In OpenMP 3.1, we actually added two new forms, write and capture for atomic. But we're not going to cover those today. All right. But basically what this allows you to do is to go and say, okay, I want to access this shared variable, all right, and I won't go into it right now, but this is actually a private variable. And later on this morning, I'll tell you about the difference between private and shared variables. So the only shared data I'm accessing here is X. And when I come in here, I can go and access X atomically, all right? I've essentially got a critical section for the accesses to X. And there's now a very restricted set of ways that you can write this access. So you can increment and decrement X, post or pre-increment and decrement. And you can also access it with any of your favorite bin ops in any way, any order you want, with an expression, all right? And this expression should only include private data, and it absolutely should not include any accesses to X. Why would you use an atomic section instead of a critical section? For performance. Why would it give you better performance? Because the compiler can turn this into atomic instruction. So if you have a fetch and increment operator, the compiler can look at this and turn this into a fetch and increment. For here, if you have a fetch and add, it can say, go fetch this shared memory location and add this data to it, all right? So your shared access turns into a single access. So you're not actually having to obtain a lock variable. You just go and directly access the shared memory. The cost of this synchronization is much lower, so it's much higher performance. Again, it applies only to a structured block, all right? That structured block happens to be very restricted as to which structured blocks you can apply it to, all right? So this is a single statement, all right, that is a structured block, all right? And each of these is actually a single statement. All right, so you've probably heard of barriers. MPI has barriers. OpenMP has barriers. Some people say OpenMP has a lot of barriers, which kind of is true. It makes things a lot simpler, and so one of the things you end up wanting to learn in OpenMP is when can you not use barriers. But so a barrier is very simple, right? In OpenMP, it means that you wait for all threads to reach this point in your program. In MPI, you wait for all processes to reach the MPI barrier call. So what happens here is if we're executing this in a parallel region, we come along and all the threads have to reach here before we start executing this for loop. And here, all right, so there actually are implicit barriers in OpenMP at the end of each work-sharing construct, which I'll explain shortly enough. But for now, just realize that we can share the work in this parallel loop across threads using this work-sharing construct. And by default, at the end of that work-sharing construct, we're guaranteed that we wait for all of the threads to finish executing the loop in a barrier. And so what if you don't need to wait? Well, then you just can add this no wait clause. And that then says, don't put that implicit barrier at the end of this parallel region, because it just adds synchronization overhead that I don't need. All right, so we've already seen how we can parallelize the Pi program using OpenMP. But we had to go and use this array in order to store the partial sum because we were avoiding synchronization entirely. And that led to us having to pad the array because otherwise we got false sharing and we didn't get very good performance. All right. Instead, we can use a single variable and use synchronization just as we did with the PThreads version. So again, we're going to include omp.h, define num threads to be 2, set the number of threads, start the parallel region, and have a scalar local to each thread to accumulate the partial sums. All right, so this is a private variable. We're going to get the thread number, find out the number of threads, and go and calculate each of the pieces, dealing them out like a deck of cards again. After we've done all of that, but inside the parallel region, we're going to have a critical section for which we're going to add values in. And so remember, though, that we lose some once we go outside of this parallel region, so we've got to do it here. All right, so here's a question for you. Do I have to use critical here? The answer is no, I don't have to use critical there. We do in this example, but we could use atomic just as easily, right? Because the way this is written, step is a shared variable, but we could create a copy of step in here and avoid that and use an atomic section as well. Yeah, it's still okay. It's a little murky, but yeah, even if you don't make a copy, Paul's pointing out. So again, now we don't have an array, so we've avoided the false sharing, but we didn't have to go through this clumsy piece of padding, which means, and we need to do that padding in a parameterized way so that we actually are aware of the size of the cache line on the architecture that we're running on. So how does it work? All right, well, we didn't do too well the first time, but now we've padded it and we've done pretty well. And lo and behold, we can go and use this critical section and have the runtime manage a lot of the complexity for us, and we do basically just as well, sometimes a little better. That's probably just variability within the architecture. But we still had to do a bit of work there to deal out the different iterations. And I kind of alluded to this already, that we have work-sharing constructs that make it so you can even more simply parallelize your code, and you don't have to be as active in distributing the work across your threads. Parallel says, I want to do this work redundantly. But sometimes you want to actually take the work and distribute it, which is what we really see in those loops. What we have are things that we call work-sharing constructs. The one that you'll see probably the most often is the loop construct. And there's some others that we'll discuss later today. I believe they're actually... All right, so the loop work-sharing construct, as I've indicated, splits up loop iterations among the threads in a team. So you create your parallel region, and then you have your loop construct. Not surprisingly, in C and C++, the name of the loop construct is for, because it applies to a for loop, and in Fortran, it's do, because it applies to a do loop. What happens is, when you come in here, each of them will execute a subset of the iterations of this loop, right? And the runtime will actually distribute those iterations for you automatically. And it will make I a private variable, so you don't have to worry about synchronizing accesses to I, all right? It will automatically split up how I covers the iteration space in your parallel, in your different threads. You could, as this indicates, add a clause, and we'll discuss those shortly, a data sharing attribute clause to the loop, to the work sharing, to the loop construct that says make I private. Now notice the difference here, all right? If we wanted to take this sequential loop and parallelize it just using a parallel construct, we're going to have to go and make a number of changes to the loop in order to deal those iterations out across the different threads. Whereas if we have a work-sharing construct, we just simply say, okay, well, create a parallel region and distribute those loops, distribute those iterations across the threads. In fact, the only changes we've made are to add the directive. We didn't have to change the original code at all. And you might look at that previous example and say, well, you know, I mean, you got a parallel directive and a for directive. Isn't that kind of a pain? And sure enough, yes, this is a frequent pattern where you want to take a loop and you want to make it the content of your parallel region. So you can go OMP parallel for and have a combined construct. Originally, there weren't very many combined constructs. In OpenMP 4.0, we have a lot of combined constructs. But the key is that they're the same thing. All right, so OMP parallel for is just shorthand for the two directives. Okay, so using OpenMP to parallelize loop, really what you're going to want to do is go and find your loops that have a lot of meat to them, that have a fair amount of computation in them. And then you want to make sure that those iterations are independent, so you can execute them in any order without loop carried dependencies, and then you just need to use the directives to parallelize them, all right, and make sure that everything has been executed, okay, and make sure that you've gotten the performance that you were hoping for. As we said, the loop control variable is automatically made private, so you don't have to worry about that. And then here, you see we had computation on J and seemed to have a dependence on the iteration that across iterations we had a dependence for J. But we can change how we compute J, and now we've removed this loop carry dependence, and now we can safely parallelize it. All right. So in OpenMP, when you put a for directive onto a loop, when you put a loop construct onto a loop, you're promising the compiler that there aren't any dependencies across these loops, so that you don't have, so that you, compiler, don't have to worry about, am I going to get any conflicting accesses based on the order in which I execute those iterations. Right? So it's important that when you parallelize loops in OpenMP that you actually can provide that guarantee, because otherwise the compiler won't do it for you, and your code will be broken. So now, a very common pattern is that we want to add things across loop iterations or multiply. Basically, we're reducing the values over the iterations of the loop. And so we're combining values into a single accumulation variable, in this case, A, B, E. And so now there really is a dependence between the loop iterations. We can't get rid of that and provide that guarantee to the compiler that, no, there are no dependencies between these loops. And this is very common. So you might look at that and go, OpenMP is not very useful. I can't parallelize that. Well, because this is actually a fairly easily parallelized pattern, it is possible. And what you need to do is tell the compiler that that's the pattern you're using. We need to be able to perform that reduction in parallel. And in OpenMP, it's very simple. You just say, on your loop, or even on your parallel, you can even have this. So if you want to do a reduction across parallel region, the threads of a parallel region, you can also apply the reduction clause. And so you just say reduction, whatever operation you want to have applied, and a list of whatever variables you want to have it applied to. And so you can do this, as I said, on a parallel or a work sharing construct. And so now what's going to happen is inside of that region that's created for that construct, we're going to create a local copy of each variable in the list, and we're going to initialize it in some sensible way. All right? And in fact, the way we're going to initialize it is with mathematically what we think of as the identity value for the operation we're performing. For addition, we're going to initialize it to 0. Inside the loop, as we go and execute multiple iterations, we're going to do the updates to that private copy. So it's as if we had the parallel region, created av here, and then had the for here, so we had different averages for each thread. But then at the end of the loop, we're going to go and combine all of these private copies using this operator that we've put in there and into a single shared value. All right? So it's important that average is actually a shared variable for this construct. All right? So now we've actually gotten that total sum over all of them, and when we get down here, we actually really compute the average. So that's actually pretty simple too. It's just a simple matter of adding that clause and identifying what are the initial values and what operators can you use. So up through P3.1, there was just a small set, relatively small set of operators that you could use. And so you could have addition, multiplication, subtraction, min. Then you also have logical operators, and in C and C++ you have and, or your bitwise operators and your logical operators. And similarly, you have similar operators in Fortran. Yeah, this evening I will actually tell you that in OpenMP 4, which was just approved last month, we've actually added support for user-defined reductions. So now you can actually define the operator you want to use and also what the initial value is. But anyway, so for the built-ins, they're all still there. It all still works the same. And in fact, when you use your user-defined reductions, it's still the same reduction clause, operator, and list of things you want to apply it to. It's just that somewhere else in your code you define how the reduction, how the operator works. But for these, you all get what you would think of as the sensible value for the initialization. And the way it's defined for min and max is it's the largest representable number in the type of the list item, and it's the least representable number in the type of the list item. Here I turn that into what you think of it as, which is the largest number and the smallest number, the other part. The more complicated way of saying it is really kind of for compiler ease of we're able to apply to a range of types. So you are already able to do reductions over vectors in Fortran. In C, sort of. All right, so anyway, back to the slide here. So we've already seen how to parallelize the Pi program in several different ways, and in particular, how to do it using single variables and stuff, all right, using a critical section. But we still had to make a fair number of changes to the code. So now that we have the loop construct, as I showed for that simple example, we can actually parallelize things with fairly minimal changes. So for the Pi program, we still have to include OMP.h, all right? We still have to create our parallel regions. Now we want to have x in here, and we still want x to be a private variable so we can access it without having to use synchronization over it. But now, instead of dealing out all these iterations, we can just use a work-sharing construct, a loop construct, with a reduction over sum. So basically, we've only made 4 changes, and we've parallelized this program. So how did we do? Performance went down a little bit. One can ask why that is. Most likely, it has to do with the fact that there's not that much work in here, and we're increasing the overhead. So just as with the parallel region, the compiler takes things out and moves it into a separate function. So for this, what ends up happening is all of this gets taken out and put into a separate function that each thread executes, all right? And then this structured block then gets removed to its own function, and the compiler makes some transformations to the way the loop indices work, and now it can now call that from each of these functions that we had that are executing on each thread. And so we've added some overhead in adding the loop the loop construct. If your loop is longer, you can amortize that overhead over more threads. Also, generally, doing things to reduce that overhead, how much overhead the runtime incurs, is an area actively being explored. All right, so now we'll just go over some more of the ways that you can synchronize, and then finally we'll wrap up with some stuff for the morning on some things for how we control the data environment. All right, so the master construct is considered a synchronization construct. We're running in parallel, and we only want code to be executed by a single thread. All right, so we can now use the master construct to do that. And that says take one special thread called the master thread and execute this thread there. And all the other threads reach this, and they just go right past it, because in the function, now actually the compiler is going to create 2 different functions, execute this one in the master, execute one that does not include that structured block in the other threads. Who is the master thread? The master thread is the initial thread that created this parallel region, so typically thread 0. Alternatively, you may not care which thread executes that code, in which case you can use the single construct. So the single construct is a lot like the master construct, except that it's not thread 0 that executes it. It's usually whichever thread arrives here first. Another difference between single and master is that we have a barrier at the end of this region. You may not want that barrier. The reason you might want to not care which thread executes it is if the amount of time it takes to do this varies widely, you may want this to be done by the first thread that reaches this point, and that may not be thread 0. However, you may not want that barrier there, in which case you can just put no weight there, which most of the OpenMP constructs that have an implicit barrier allow. You'll recall that I said you need to remove all the loop carried dependencies from your code, except that sometimes maybe that's not possible, and sometimes maybe the loop carried dependencies aren't actually just simple reductions. And I won't try and say what necessarily here is different, but nonetheless, what you have is the ordered construct and the ordered clause, which now says this part of the loop I want to have execute in exactly the order of the iterations. And so you put the ordered clause on your loop directive, and that now tells the compiler there's going to be some stuff in this loop that has to execute in exactly the order of the iteration space. Everything else can execute whenever, I don't care, but this has to execute exactly as ordered. And then in each iteration, you will execute the prior part of the loop in that iteration first, but then in addition, this statement won't execute in iteration I plus 1 until it's executed in iteration I. And that's because we've now put it into the ordered construct. Again, in general, though, this is something you want to avoid. So to the extent that you can change your code not to need ordered constructs, you want to do it, all right? Because this is basically saying stop executing in parallel here. So there are several lock routines that are available for synchronization. Each lock, it's very similar to pthread mutexes. You're able to say, acquire the lock here, and anything I do in here is now protected by that lock until I free the lock. You have simple locks, which means that basically you're not going to end up acquiring multiple nested locks, and you have to initialize them, you can set them, you can unset them, you can test them, and then you can destroy them. And similarly, you have ones that can be nested, and they have separate functions. Anyway, so you don't need to worry about any flushes or anything like that, but I haven't told you about flushes yet, so I won't try to worry about that. Here, we're going to create a histogram. What we want to do is now access this histogram, each of the elements in the histogram, with mutual exclusion, but we want to avoid so we want to avoid race conditions to the individual elements, but we don't want to have a critical section that locks the entire histogram array. So what do? I create a lock for each element, and then when I get into where I'm going to update that histogram element, I acquire the lock for that histogram element, I update it, and then I free the lock. All right? And so I'm now assured that I have mutual exclusion for that update. And then at the end, I have to free the locks. All right, well, as I mentioned, there are a number of runtime routines available in OpenMP, so we can set the number of threads, we can get the number of threads, we can get my thread num. We've seen all these already used. I can also find out what's the maximum number of threads. So many times, OpenMP runtimes are designed so that you can only have one thread per hardware thread. Some runtimes will allow you to overload hardware threads. All runtimes set some maximum total number of threads that you can get. This routine lets you go and find out what that maximum is. And that tends to be useful if you want to do nested parallelism, all right? Because then you want to think about how many threads do I want to use at the outer layer so I then have threads available at the inner regions. Another call that we have is OMP in parallel, which tells you, are you actually in a parallel region? The reason you might want this is if you were writing a library, you might want to know whether or not you're already executing in parallel. You might not want to create a nested parallel region. So then we have these routines that say we can tell the runtime we want to, within some limits, strictly enforce how many threads are created, and we want to find out what the current value of that routine is. And then we can also find out how many processes are in the system. There's many other routines. We've added probably another half dozen or more in OpenMP 4.0. But if you have these, you're going to be able to handle a large number of cases that you'll want to do initially. How many threads does a parallel region execute? And the answer is, well, it depends. If you go and look at the OpenMP specification, you'll find that there's a complicated algorithm that tells you how to figure out how many threads your routine executes. And in part, it depends on whether or not you have the internal control variable for dynamic parallelism set to true or false. If it's true, then at each parallel region, the runtime is allowed to decide, I think that this parallel region should get this many threads. So if you want to enforce, to some extent, how many threads you're going to get, you want to set that to false. And now here you can say, okay, I want one thread for each of the processors. And now I can go and get the number of threads, and I can get my thread number as well. So OpenMP has a concept of internal control variables, which are variables inside the runtime, or conceptual variables inside the runtime that control how OpenMP works. So if you make this call, you'll set the internal control variable to that number. However, when the runtime goes to execute this parallel region, it has to determine how many threads it will use. If you don't have dynamic set to false, it's immediately allowed to ignore that internal control variable and choose however many threads it wants. If you do have dynamic set to false, you still may get fewer threads than you requested. Well, suppose I set this to 1,000 and I only have 4 threads. I only have 4 processors, and the runtime says max threads is 4. Well, it's going to say, well, fine, you want 1,000 threads, I ain't got 1,000 threads, you get 4. Depending, in this simple code you won't see it, but you might have multiple parallel, you might have nested parallelism. And now you may not have threads remaining, even though you set it to 4, but you create a parallel region with 4 threads, and now in nested parallel region you try and create another region with 4 threads. I don't have any threads left, so I'm going to give you 1. All right. Maybe you created a parallel region with 2 threads. You try and create a nested parallel region with 4 threads, and it says, well, I got 2 left, so I'll give you 2. So as a general rule, that's why it's often a good idea to find out how many threads you actually ended up getting, at least if your code actually really depends on how many threads you got. As was kind of already indicated, we do have a number of environment variables in OpenMP that also control how the one of the ones you'll probably use most frequently is OMP num threads, and you can set that to an integer value that says use this many threads in each parallel region. And it actually is a little more complicated, and we'll get to that in a second. You can also set the size of the stack in each of the threads that gets created. All right, now that creates the child threads stack size. So that initial thread is not governed by this variable. What do idle threads do? Well, so first of all, something that's kind of important to realize is that in the pthread program, right, we created those threads, and then when we joined them, they were all destroyed. So each time in a pthreads region that we create a new parallel region, we're creating a whole bunch of new threads. So we have this overhead each time of creating new threads. Well, if you think about it, really you could just synchronize across the threads and say, oh, you finished your work, I'll now execute back in one thread, but I'll leave the other threads sitting around so I don't have to recreate them. Well, that's actually what all OpenMP runtimes do. So now you have these, once you've encountered one OpenMP region, you've created your threads, and now you've got these extra threads sitting around in your process, potentially consuming resources. If you got extra processors, it's not really a problem. They're just sitting there spinning over on some other processor. And so you probably want them to stay awake. And this holds true at barriers and locks as well. You want them to just sit there and spin. However, because they're also going to sit and spin on locks, that may mean that they generate memory accesses. So they may actually consume some resources that are shared. And so you may want them to be passive. And so basically you want them to go to sleep and stop spinning. And so you can set them to be passive. In the next session, Paul's going to go into schedules for loops. I'm not covering that here, but there is an environment variable that lets you set the default schedule. All right, so I've kind of mentioned that we have this concept of data environment and data sharing attributes for variables. All right, but I've avoided so far getting into a lot of details about it because we didn't really need them. Some variables are shared, some are private, and as I indicated, there's sort of defaults for them, and in general, you can often rely on the defaults, although it's not always the best practice because you might actually want to be explicit about what the data sharing attributes are. So that way you make sure you're getting the attributes you want. All right, but as I said, most of the variables by default are going to be shared. All right, so global variables are always shared. So in Fortran, your common blocks are shared, save variables are shared, your module variables are shared. And C, any file scope variables are shared, static variables are shared, all dynamically allocated memory. So if you use malloc or new or allocate, that memory is shared. All of the threads can get at it, and you have a pointer to that memory. You can just go and modify it in a shared way. However, not everything is shared, and as we've already seen, there are many instances where you don't want things to be shared, because if you have private copies of them, you can get much more efficient programs. So in OpenMP, we try and define things as not shared where it's pretty clear that sensibly you don't want them to be shared. So stacked variables are private. And so this means that when you're in a parallel region and you create a new variable within that structured block, you're guaranteed that it's private, which is probably what you want, because you're creating different variables in each of the structured blocks. Anyhow, and then any automatic variables within a statement block, as I said, are private. So you get a bunch of things done for you that are predetermined sharing attributes. So here's an example. A and index and count are all shared. Why are they shared? These are global scope, right? They're file scope, and this is static. Temp is local, private to each of the threads. Why? Because it's declared within that function, all right, that's executed within the parallel region, all right? And so then graphically, we create these shared variables out here, and we get private variables in each of the threads. So how do we change sharing attributes? What we do is we use sharing attribute clauses, all right? And we have a number of different clauses. So we can define things as being shared, private, or first private, and they apply to the construct, not to the entire region. All right? So the construct on which we put that clause is the scope in which that variable is shared or private. All right? So we're creating a data environment with each of these constructs that we encounter. If we want to save that last variable of a loop, the last value from the value from the last iteration of a loop, we can declare a variable to be last private. So it's still private, but we get to have that last value transmitted back to the outer shared scope. And you can override the default attributes by setting the default to private or shared or none, but you can only do default private in Fortran. You can't do it in C and C++. And that has to do with the issues of pointers and things like that in C++, making it very difficult to make everything private by default. All right, so as I've indicated, the private clause is going to create a local new copy of each var for each thread. And when you say that it's private, it's uninitialized. So even though maybe it existed out here and we initialized it inside the parallel region, it is not initialized. If we go in there and we start adding to it, we've got some undefined initial value, so that's probably not good. So what if we really want to just write the initialization once, but we want to make sure that it gets propagated to all of the private copies? That's when we use first private. All right? So first private says, I want a private copy of this variable inside this loop here, but I want it to start out with the initial value from outside the loop. All right? And so when the compiler creates this initial variable, this private variable for you in here, it will initialize it for you properly. All right, and I already kind of covered this where I said, what if you want to save the value of that last sequential iteration, all right? So it's the logically last iteration, not necessarily the last iteration to execute, because they're executing in parallel. You just define it as last private, and then you'll get that value back. And so now we can go and make almost no changes to our original Pi program and parallelize it using OpenMP, because now we can say that X is private, and so we no longer have to go and create X inside of this region. Right? Otherwise, this is the same as the previous version. Anyway, so yeah, so in general, it's good to use reductions because they're usually pretty scalable. I is private by default. But now we've only gone and added two very simple lines to our serial program, and we've gotten a parallel program that gets fairly reasonable speed up. So OpenMP really is very easy to use, at least in its most basic forms. All right, so there's now a lot more available to you in OpenMP, and so there's a lot more power in OpenMP. And we'll be talking about some of that stuff later today. Primarily the first session this evening will go into some of the new power that we have in it. Although Paul will be covering the tasking stuff, and that's another area where it gets a little bit more complicated. In general, you can get a fairly far way using OpenMP, using the very simple constructs. And really, you can think about the problem that you want to solve rather than how you're going to parallelize it. And so after the break, Paul will go and cover some of the more advanced features and also some of the issues in getting good performance out of OpenMP. So I do have to warn you about that. OpenMP is very easy to use and to get introduce parallelism into your code. As you saw with some of the even early examples of how to parallelize that Pi program, sometimes that simplicity means you don't get very good performance. And it's not that you can't get good performance out of OpenMP, it's that you have to think a little bit more and work a little bit harder to get performance out of it. All right,